So here's a little mini review on solving differential equations by separating the variables. So if you have a dx dt with x of 0 equal to 3, what do we know? Well, we can get the dx and the x on one side and all the t's and the dt on the other side. Now there is no t in this one. But since the dx is on the top, moving that x over to the other side will give you 1 over x. Then integrating both these sides, the one side is the natural log of x, the other side's integration would just be t, and you have a plus c. And with that initial condition, we'll be able to solve for what c is. Now, if you have a natural log, you could get the x by itself by changing to exponential form. Oops. Remember this idea of exponent laws, that if you have t plus c, this is really e to the t times e to the c. And technically, this is a constant. So we can just change it to our new value of c. And this should bother me a little bit, and it does. Sometimes I like to write c1s along here because that works out. And then I have a new c that's different. I could label that one as c2. But like I said, with the value of c, it's kind of a common understanding that it's some number, and we can just sort of like not worry about it until the very end. Now I can plug in 3 for x, 0 for t. And get an equation. So the idea with a differential equation is often we have to separate the variables. We look at our example 2 here. We got a dy dx. So if I move the dx over to this side, I would have 2 dx on this side. I would also need to move the x squared plus 1 over to the other side as well. And this is good for us to recognize the tan inverse, because a lot of our advanced techniques that we started off the beginning of this unit used our inverse functions. And from here you can plug in the value. Tan inverse of 1 is pi over 4. So you can solve for c. So I'm going to let you try that third one on the bottom on your own. The variables have already been separated. All right, I'm going to put up the answer to that third one, and you can check it. So a couple things to note in this one. It was already nicely separated, so the integration was easy. But in solving for y, you have to square root both sides, which involves making sure you have the plus or minus. Okay, we put in our initial condition and solve for c, and our initial condition right here tells us that when x is 3, y is positive 5. So you need to show the plus or minus and then know to only take the plus. Okay? If we think of common mistakes, a common mistake is forgetting the plus or minus, right? And in this case, forgetting the plus or minus, you would have been actually okay after the fact. It might be that you lose a mark partially through because you didn't have a plus or minus. And if I was predicting on an AP exam, what's the best way to see if you remember the plus or minus? To make the y negative, so only the negative one is the one you keep. Because that's a lot less likely and a lot less, it's something that doesn't happen as often from your earlier math. So then if you make the common mistake of forgetting the plus or minus, you also make the secondary mistake of not making sure that it was negative. So I would say that's probably more common on an exam because they're able to check deeper understanding that way. So the fact that y is positive tells us right here only to use the positive one when solving this and not the negative one. And same thing, when we write our final function, we don't have the plus or minus, we only have the plus there because our initial condition told us that the y had to be positive. So these were all particular solutions. They gave us an initial condition. These next couple questions are just asking us to find the general solution. And one thing to sort of help you with these equations is when thinking about separating the x and the y, things have to be sort of multiplied. Like I can't just move the 2y over and leave the 1 on this side. I need to divide that whole 2y minus 1 over to the other side. Sort of as an initial step here, if I just separated the dy and the dx by moving the dx over to the right side, that 2y minus 1 would have been in brackets. And I can't just move the 2y over to the other side. I need to move this whole thing. So with separation of variables, you are always trying to get things into a multiplication and division scenario. So when you're separating the variables, there's no extra adding that needs to be done at the end, because that actually doesn't work in these situations. This would be a natural log, 2y minus 1, but it would have a simple chain rule where you'd have to multiply by 2. So remember, we have to compensate that by dividing by 2. And there would be a plus c on that side. Now, if I multiplied by 2 to get rid of my fraction, that would multiply the x by 2, it would multiply the c by 2. So if I was numbering this, this one would have been c1. This is my new c, this could be c2. And again, on the exam with the c's, they're a little bit lenient with that. Can change it to exponential form, 2y minus 1. If I take the absolute values away, it's like having a plus or minus there. E to the 2x plus c. This is still my c2. This would technically now be my c3. Because this with your exponent laws would be e to the 2x times e to the c, and this e to the c could just become a new number c out in front. And then finally, we can move the 1 over and divide by 2. And this is a general solution, yes.
Would it even matter having the plus or minus if c could be any real number?
True. At that point, c could be positive or negative, so the plus or minus doesn't matter. It's just more of a, when you have the absolute values and you take them away mathematically, it could have been a positive on that side or a negative. In this situation, you're right. That doesn't actually affect it. So this one's interesting because if I just first think about moving my dx over to the other side, I'm adding. And adding doesn't work well for separation of variables. And if you can't separate the variables and integrate both sides, the best you could do is draw a huge slope field and hope that you could draw the function using your slope field. And drawing slope fields is really tiring and monotonous because you have to figure out every single slope for every single point separately and then draw a tiny little dashed line. But here, if I factor out the y, I can change this from adding to multiplying. And with the multiplication right here, my x and my y's are separated. So that lets me move the y to the left by dividing. I move the dx to the right. And then I can, again, integrate both sides. And again, with that plus c there, you could break it up with your exponent laws and think of that as multiplied by e to the c. Because your exponent laws, if your bases are the same, you add the exponents, right? So if I added those exponents together, I would get exactly what I have here in this box to start with. And then thinking that e to the c is another number, I could just bring that c out in front. And once again, the plus or minus wouldn't matter because c could be any number. So algebraically, what is tricky is figuring out how you're going to separate the variables. So you have this e to the x minus y. You need the y on one side and the x on the other. So how do we think of doing that? Again, thinking of your exponent laws and separating that to be e to the x times e to the minus y. Now I'm multiplying. One term has x's, one term has y's. This will allow me to bring the e to the y to the other side and the e to the x over here. One in-between step that I did here, right? If I move the e to the y to this side, do you see that it would be e to the negative y on the bottom, right? Because I would have to divide. And a negative exponent law says if you have a negative exponent, you can bring it to the top. Or some people would have started and could have written that way as well. E to the x over e to the y. Either way, it lets you bring your y's to one side and that e to the negative y, bringing it to the top. These are both very easy integrals to do. And we get our plus c. if you want to get y by itself, you would have to take the natural log of both sides. You could bring the y then out in front. Natural log b is 1. And we're going to end with part of a long answer question. Make this bigger for you guys to see. Part of a long answer question came from the exam in 2001. Ooh, 25-year-old question. The function f is differentiable for all numbers, okay? Something that from like 5 units ago, differentiable means it is also continuous. So if something is differentiable, it implies continuous. The point 3 comma 1 over 4 is on the graph of y equals f of x, and the slope at each point is given by this differential equation, which has a y squared and an x in it, so I start thinking separation of variables right away. Find the second derivative and evaluate it at the point 3 comma 1 over 4. So we've got the first derivative. If you were finding the second derivative, do you see that you would have to use implicit differentiation? So there's my dy dx. So my second derivative, d squared y over dx squared, would be keep the first the same, derivative the second, product rule, plus keep the second the same, derivative of the first, and the derivative of the first, well, that would be a 2y, but because it has a y, implicit differentiation says we have to use the chain rule and multiply by dy dx. And since you know what dy dx is, you can substitute, put it in the green box here, I can substitute this in for dy dx, because I already knew that from the equation. Again, you do not need to simplify on a long answer question. This here would have been completely right for full marks. In fact, they would probably give you this completely right for full marks for the d2y dx squared, but in order to evaluate it at 3 comma 1 quarter, you do need to change it to the next step. Now we can plug in 3 for x, 1 quarter for y. Here's some notation for you. The second derivative straight line evaluated at this point. And you get negative 1/8. So you'll see this, like, this is only part of this question, A and B. C and D probably would have used maybe the unit that's coming up or some other units to review that I didn't want to review at this time. But on the long answer questions on the exam, they like to cover a lot of units in one question. So you see how part A is checking your implicit differentiation. Part B now is checking if you can separate your variables and integrate both sides. So we can move the y squared to this side, the x to the other side. And since you have the initial condition of 3 comma 1 over 4, you can solve for C. And then once you solve for C, could you get your y value by itself? Absolutely. Do we need to get y by itself? Yes. Look at the original question. I'm going to scroll up, I'll scroll back down. But this part of the original question says, find y equals f of x. In other words, find y equals something by itself. So you did have to do the algebra to move things over and to solve. Does this last step make sense? Technically, you could multiply both sides by y and divide both sides by the x squared minus 6x plus 13. Or you can, anytime you have a fraction equal to fraction, you can flip both sides. And you get your final answer.